All right, in this last chapter, we're going to have a little introduction to calculus. And it says exploring limits, derivatives, and integrals. And I'll explain what these words mean at the end. Calculus is one of those things that has sort of an aura to it. A lot of students think of calculus as very hard math or something like that. On the other hand, most students who have not had calculus would be hard put to tell you what calculus is about. It turns out calculus is about two problems. The first problem is, how do you find the slope at any point along a curve? All right. Now, slope for straight lines, you know how to do it. It's rise over run, delta y over delta x. What we're wanting to find is what is the slope when what we have is a curve. So the vertical axis in this problem, as it's illustrated, represents displacement or movement from some starting point along a line. And the horizontal axis represents time. So if I go back to when t equals 0, or the time equals 0, I'm at the y-intercept here. And so this point would be my starting point. And so what we can see in this problem is that this object, whatever it is, person, thing, car, who knows what this is describing, but it's moving forward along this axis fairly rapidly at first, and then in this interval here it's moving forward rather slowly because there's a long period of time and not very much movement forward during that time. And then here the speed picks up again, and up here it's going steeper, which means more distance is covered for a smaller period of time. So we can interpret the slope of this curve as how fast we're moving. And in fact, that's pretty explicit, because if I find the slope, I'm finding rise over the run. This measurement is a measurement of displacement. That's how far something travels. This measurement is a measurement of time. So if I take the ratio of distance over time, that's speed. And so in this case, the slope of this curve has a very concrete physical significance. This represents the speed. And you can imagine if I have a collection of data or some mathematical relationships that tell me where I am as a function of time, you might want to go back and actually calculate how fast am I moving as a function of time. So the first task in calculus is, if I have a function which gives me this variable as a function of this variable, can I come back and find a second function which gives me the slope as a function of this variable? In this case, we're talking about time here. So if I have displacement as a function of time, how do I come back and find velocity as a function of time? In this second problem, this axis represents velocity. And again, the horizontal axis represents time. What I might be interested in is the area under this graph. And if you look at the dimensions of area, it's going to be height times width. And notice that the height of one of these rectangles is a velocity measurement. The width is a time measurement. And if I multiply velocity times time, I get a distance. And so this area here represents a distance traveled from time A to this little time here. Okay, we'll look at that in more detail in a minute. But it turns out that the area here gives us our displacement. Look at these two problems for a minute. Here it gives us a way that if we know displacement as a function of time, we can calculate velocity as a function of time. Here, if we know velocity as a function of time, we can calculate displacement as a function of time. So these are actually inverse operations of each other. They come as pairs. And this is one of the fundamental insights. These two very different looking problems are the reverse of each other in very much the same way that division is the reverse of multiplication, that finding roots is the inverse of finding an exponent, that subtraction is the inverse of addition. It turns out that this process of finding a derivative, which is the slope as a function of time, and this process of finding an integral, which is the name for, I haven't mentioned it, that's the name for finding this area under a curve, these are actually inverse operations. And by the time we get to where we can demonstrate that, That's actually known as the fundamental theorem of calculus, that derivatives and integrals are inverse operations of each other. So this pair of problems is actually two sides of the same coin. The process of achieving our goals on these two both involve limits. So we're going to play with the idea of taking limits as a way of finding slopes and areas under curves. The text gives you a series of pencil and paper problems for doing this. I'm going to approach this using GeoGebra as a way of walking through the same set of concepts. I think it's a good idea if you actually do the pencil and paper process, but perhaps using GeoGebra is a little more fluent way to actually come to understand these ideas. So let's look at those now. Okay, the first concept we need to work with is the slope at a point on a curve. Now, up until now, you know how to find the slope of a line. So if A and B are 2 points on this red line, we can find the slope by taking the rise over the run. Now, as I've labeled them here, the vertical axis represents distance, and I'm representing distance as delta x. You could use the delta y if you like, whatever. And the horizontal axis I'm representing as delta t. The delta, this is a Greek letter for the D sound in Greek, but it stands for difference. So the little triangle is a capital D in Greek, a capital delta. So between A and B, if I take my distance over the time, it gives me the speed. So the slope from A to B is the slope of this red line, and that would give you the speed that's represented by that line. What we're interested in is the slope of the curve, and the question is, how do we get that? Well, you might say, well, let's bring these 2 points together so we can find the slope right there. But look what happened. It disappeared. And why did it disappear? Because look what delta x is, 0. What is delta t? 0. You know you can't divide by 0. However, remember the distinction between a non-zero number divided by 0, which we say is undefined, and 0 divided by 0, which we say is indeterminate. Delta x over delta t does not exist at this point, but it's not simply undefined, it's indeterminate. So we need a different way of getting at this. So let's come back here and notice that if I take 2 points that are separated, I only have an approximation to the slope of the curve. This one's too steep. Down here it's not steep enough. Okay, and so in order to find the slope of the curve, I'm going to be close to the slope if these 2 points are close to each other. But we're dealing with approximations all the time. Let's zoom in. Notice that as we zoom in, okay, the curve itself looks flatter, just like the Earth seems like it's flat if you're dealing with a football field, even though it's curved if you're looking at the entire country, for instance. So as I continue to zoom in, I get a better and better approximation, and my delta x and my delta t are becoming tiny. Over here I can see my delta x and delta t. The text representations on the screen have zoomed out of the way, but look at this. So delta x is 0.0001 at this point, and delta t is 0.0003. Let's come up here and increase the rounding to maybe 10 decimal places. So again, we have 2 numbers that we could divide, and we would get a slope between these 2 points, which is not exactly the slope at A, but it's close to it, because B is close to A, and this curve looks flatter and flatter as we get closer. All right? So this is sort of the, let's go in further, and you can see that the closer we get, the better the approximation is. Let's see, right up here is our slope. Now, by the way, I noticed something here. It says slope limit. That's something we haven't mentioned yet, but this program is actually able to calculate the limit of the slope, and that's what we're going to do. what is the limiting value as b approaches? Remember, we've talked about limits for sequences. As this point here gets closer and closer, you can think of it taking on a sequence of values, and it's not any one particular value we're interested in. We're interested in what is the value it's approaching as it actually approaches a. We can't say what is the value when b is sitting on top of a, because then you have 0 over 0. We're interested in anything just short of that. Okay. Notice how good our approximation is at this point, by the way. 0.41589, and here's 0.4158888. So we're getting close. It still has a few digits to go, but if I zoomed in sufficiently, this approximate slope would eventually converge to this, the limiting slope. As I zoom in, we should get even a better approximation. Here's 888, and then this one is different here at the 6, and here it's the 3, so it's still off there. I could keep going. Okay, but let's come back out again. Here I'm just zooming out. Okay, I have to zoom way out. I went way in. Okay, so despite the fact that let's go out to there and let's center this up. Okay, despite the fact that all we have to work with are approximations, if I take a sequence of approximations such that b approaches a, and if I can find a limit to that sequence, I have a way to assign a value to the slope at a point. That's the key, and that's the essence of what we're going to be doing when we do this process. All right, it's called taking a derivative. We're going to take our function f of x and we're going to find a derivative function. We're going to derive a function from this f of x that will give us the slope at every point along the way. Finding the slope at this point, we might do it by approximating it using a graphical technique or something like this. What we're going to do in calculus, and in this introductory section we'll do it a little bit, is be able to actually figure out a new function derived from the original function, so that for every point on our domain, instead of knowing the distance, then for each point along this domain we will have the velocity. And that's a derived function, a function derived from this, and it's called the derivative function. Let's look at the significance of area under a graph. Here's a graph, and the function I've put up here is very, very simple. It's simply a constant function. So g of x equals 6, and that's this blue line here. So what is the significance of the area under this curve? If we are plotting velocity versus time, velocity, you can sort of think of it as speed. There's a slight subtlety difference, but take physics and you'll learn all about that. If I'm plotting velocity versus time, then my vertical measurements have units of speed, meters per second, miles per hour, whatever the units of speed are. My horizontal measurements have units of time. So let's look at this area. If I take an area under this graph, the area is given by the length times the width of this rectangle. And so this dimension is, in this case, 6 meters per second. And this horizontal distance is 7 minus 2. This is 5 seconds. So if I take meters per second times seconds, the seconds cancel, leaving me meters. So when I'm plotting velocity versus time, the area under the graph gives me meters. Okay, here's another graph of velocity versus time, but our function is no longer just a constant function. In fact, it's a cosine function up here. It could be anything. It could be a polynomial, exponential, logarithmic, whatever. In this case, we have a cosine function. And let's interpret the area under this kind of a curve. Well, first of all, notice that we can approximate the area by these little bar graphs. So in other words, if you were to calculate this area, one approach might be to choose points evenly spaced along this curve and take finite differences between here and so forth. If I evaluate the function at these points, say the midpoint of this first segment here, and say what is g of x at this point, that's the height of this rectangle. And then if I take my gap width here, then I can take the length times the width, the height times the width here, and get an area for this slice. We just saw that the area under a velocity versus time graph, if it were constant, is velocity units times time units. So this little slice right here would be a distance. This would be the distance, or an approximation to the distance traveled in this first, see if this is 2, 3, 4. So this is 1 second here. So the distance traveled in this 1 second would be given by the area of this little bar on the bar graph. The area under the second bar is the distance traveled between second 3 and 4. The area under this bar is the distance traveled between the 4th second and the 5th second. And the area under this is from 5 to 6, and from here is from 6 to 7. So the sum of these areas would be an approximation to the area under the curve. And you can see that since each one of these represents a distance, the sum of these would be the overall distance. Now, you might object, this is not a very good, it's sawtooth, it's supposed to be smooth. Well, one way we can do that, notice the D here is how many intervals I've put between 2 and 7. I've chosen 5. If I bump this up to 6, then I have 1, 2, 3, 4, 5, 6 widths there. And that's a better approximation. The sawtooth is not as extreme because I have more closely spaced points along the curve. So let's increase it some more. Let's go up to 10. Now you can see that the sawtooth is getting a lot smaller. And what we're seeing is that the area, let's see, look at the area. If I started off at 5, it's 22.2532. By the time we get up to 10, it's 22.2361. Okay, and if I keep on going, so look at this number, 22.236, 23 various things. It looks like 23 is stabilized and we're only changing way out here. By the time we get up to 20, we're at 22.2318. And notice that the sawtooth has been minimized quite a bit. In fact, those little overlaps above the curve and the little overlaps under the curve probably mostly cancel each other. But they're not exactly canceling because this is curved. But we can make those smaller by taking more intervals. What we can do again here is take a limit. All right? And notice this limiting value over here is 22.2304. And here's the 22.2318. So again, we have a limiting process. If I take a sequence of results found by taking thinner and thinner slices, it's no one result that we're interested in, it's the limit of the sequence of results. So if I divide this into more and more and more pieces, and we find those areas and we say, what's the limit that this approaches? That is how we're going to define the area under the curve. So one of the things that these two kinds of processes have in common is they're both based on limits. We can't find the area under a smooth curve by simply dividing it up into little pieces because we can only approximate it. But we can make the errors smaller by going to smaller intervals. And by the time we get down to infinitesimal intervals, we can think of the fact that we're approaching the actual area under the curve. We take the limit of this summation of these little intervals. Okay, before we quit, I'd like to introduce a little bit of notation here. Let's take the case where we're dealing with a slope first of all. If I want to find the slope of a function at some point A, the way I do it is I take a second point B, and I take the slope from A to B. Now, if our axes here are x and y, this is called delta y, and this is delta x. And the rise over the run gives us a slope there. So the slope is delta y over delta x. Now, I'm not interested in the slope from A to B. I want to know the slope at point A. And so to do that, we do what we did graphically earlier. We let B slide down until it approaches A, and we take the limit as delta x approaches 0. And so we take the limit of this ratio as delta x approaches 0. And that is what we define as the slope at A. Now, we give it a new name instead of this cumbersome notation. We call it dy over dx. Notice that delta y and delta x are referring to these finite differences between 2 points. Dy and dx, in fact, this entire symbol is sort of like a unified symbol for this whole expression. So instead of writing this entire expression, I can write this, and I call this the derivative. Okay, so the derivative is the limit of the ratios of these two differences as B approaches A, essentially, as delta x approaches 0. Okay, so this is the terminology, but when you use the dy over dx notation, it's actually referring to this entire construct. It's a ratio which is then taken to a limit. Okay, if I want to find the area under a curve, let's label these axes x and y, and say that here's my curve, and I want to find the area between two limits, A and B. So I'm looking for this. The way we do it is we think of a series of strips. Okay. And so for each one of these strips, the height is the value of the function. So if this is f of x, the height of one of these strips is f of x. F of this value gives us that height, f of this value gives us that height, and so forth. And so what we're looking for is the summation of our f of x times the width. So the height times the width to get the area. Well, the width we're going to call delta x. Okay, for the x-axis like this little gap is our delta x. So the sum of our f of x times delta x would give us the sum of these strips, which is this approximation to the area. But I'm not interested in the approximation to the area. I want the actual area under the actual curve. And to get that, we take the limit as delta x approaches 0. And this is what we call the integral. Okay, between these limits from A to B. So say A to B. All right. Again, we introduce notation to simplify the notation, but it means exactly this. Okay. Instead of using the Greek letter for S, we use the English letter, sort of written, stretched out like that. And so once I've taken this limit, I use this S for the summation of f of x. And instead of using delta x for a finite difference, we've taken the limit, and so we call it dx. And we take that from A to B. And so this notation is shorthand for this notation. This refers to the limit of the sum of the height of the function times the width of the strip as we let the strip go infinitely thin. We let the width of the strips shrink to 0. So this is notation you'll see in a lot of calculus textbooks. You may have wondered what that means. This is a symbol for this larger, bulkier notation, which simply means take the areas of the strips, height times width, take the sum of those from A to B, and take the limit as our delta x shrinks down towards 0. We call the result integral of f of x dx. Okay, this is pretty much an overview of calculus in one short lesson. You've been introduced to the derivative and the integral You've seen how we're going to get at it using limits. What you haven't seen are the techniques that we use to actually carry out this process. And so that's what's left to do.